Pleasure to introduce Yuriy Drozd, who is going to speak about construction from commutative surface singularities.
Thank you. So I'll start with some historical notes about study of Cohen-Macaulay models at all and non-commutative case especially. First, the well-known remark if we study Cohen-Macaulay model, if we study something in representation theory, for instance, Cohen-Macaulay model, vector bounds or something, then there are three types, three cases. First, always is finite case, finite type. But clear, finite and many decomposable objects. Usually all objects are decomposed into decomposable, sometimes it's even unique and so on. That's clear. But then, in infinite, there are two cases, the same type. I suppose that we have something like geometry, so we can consider families of objects and so on and so on. Then there are only one-dimensional families of indecomposable objects. And very interesting is that wild type. And there are two concurrent definitions of wild type. I will start with geometric. Geometrical means that there are families of indecomposables of arbitrary big dimensions. That's more or less clear. And concurrent algebraic by the way it was formulated earlier than geometrical one. For any finitely generated algebra, okay, there is exact functor from A models to our category representations of vector bundle and so on, which reflects isomorphism. That means maps non-isomorphic to non-isomorphic. Yeah, more or less obvious that algebraic implies geometry because for A models rather big algebras, there are families of any dimension. The question is whether always geometrical definition in practically all known cases that's so, but there are no special reason why. Okay, that's the main definitions. Now, what is known? I recall what is known. First, for curve singularity. I will speak, for instance, about singularities or algebraically closed field and, if necessary, characteristic zero. Finite type is completely described, was completely described in 1967 by Jakubinsky and Reuter and myself. And a bit later, I guess 1955, Knorr and Buchweitz, Groer, Schreier established relations with the singularities. Namely, they showed that curve singularity is of finite type if and only if it dominates some of the singularity. Dominates that there is birational finite type. Okay. And tame type and wild type was described by Groer and myself. And the result is a bit like that of Knorr. How a singularity is tame, or Cohen-Macaulay tame. Tame with respect to Cohen-Macaulay modules. If and only if it dominates a singularity of type typic X3 minus lambda X squared. Well, so for curve singularities, everything is more or less clear. Certainly, there are problems how to in this case, all Cohen-Macaulay modules were effectively described. In this case, it is not so. It is put that it is tame, but to describe explicitly, for instance, Cohen-Macaulay modules over this singularity, I'm not sure. I know it for 4 case. Yeah, it's one of the simplest one, and partially for 3.6. I think that okay. This is about curve case. Then what about surface case?
I have a question. In this curve case, the y,
Sorry?
the y geometric coincides with y algebraic in the case of curves.
No. I don't know whether geometric implies.
Even in that case.
No. In this case, yes. I say that in practically all cases, you see, the thing is that, for instance, Groer and myself proved namely algebraic case, and then we obtained geometry immediately. Okay, I will say, I will especially show when I don't know. Okay, surface case again, finite type is known. It was told by Enno and Auslander. They proved that finite, at least in characteristic 0, is the same as quotient. That means we must take this and F G is a finite subgroup. Then there is mathematical correspondence and so on and so on. So that finitely sub. For 10 gains is now more or less done, but not completely, I guess. Namely, that was when Kahn proposed his construction. He related Cohen-Macaulay modules over a singularity with vector bundles over some projective curves. Maybe even reduce it, not necessarily reduce. In good cases, they are reduced, but it is not programmed. Okay. Then, and he also showed, it was, I guess, in 1987, he also showed that so-called simple elliptic singularities in the notations of some are taken. I recall simple elliptic means that exceptional cycle of the minimal resolution is an elliptic curve. Using Kahn reduction and our result with about vector bundles of curves, Yuriy and myself also proved that if the singularity is minimal elliptic, which means that it is Gorenstein and dimension of 1 P star OX tilde is 1. Yeah. Then it is prime if and only if the exceptional cycle is either smooth elliptic or so-called Kodaira cycle. That's intersection of several projective lines. It might be 2 projective lines or it's an intersection of 1 projective line. Yeah. Okay. Otherwise, what? Then Fernandez Bobadilla and Romano Velasquez. Showed that if singularity is Gorenstein, no other same cases, and it is geometrically viable. In this case, I don't know whether it is algebraic, but yeah, it's a question. I think so, but I cannot prove it now. Okay, so it's more or less all known for curves and surfaces. There are also results for rectangle surfaces, but I will not mention them. Okay. Now I go to non-commutative case. No, not commutative. Actually, what is non-commutative singularity? Non-commutative singularity is something like this. We have regular complete local ring. And suppose even regular. And we have A, our order in a semi-simple algebra. Over the ring of what is in the and this is what is non-commutative singularity.
Could you refer what is an order in
Yeah. And usually R in geometric case R is
So there is a question. So what is the definition of R order?
oh, that means an A algebra, R algebra, finitely generated as R mod. And as it is in algebra, it is torsion free. Usually we suppose that it is Cohen-Macaulay. That means free. Yeah, usually free as R mod.
So non-commutative.
And as it is a semi-simple algebra, it means that it contains no important attributes. Okay, that's what is non-commutative singularity, shortly speaking.
For those of us that never saw an example,
Sorry?
can you say one example for those of us that never
Oh,
saw one
I will show some examples.
So my favorite would be the group algebra.
Yeah,
All
for
the-
instance, group algebras, then one
group
in the, it is an interesting example. Consider the into 2 by 2 matrices. The set of matrices of this R, U R. It is an interesting example. Why? It is regular global dimension of A is 2 just, but not maximal. Certainly it is a bigger order. In commutative cases, regular implies normal, implies integrally closed. It is not in a commutative case. Okay. Then, again, finite type. An interesting note. An interesting note. Curve case. Is not completely done. Completely done. Even for finite type. There is no, I don't know it. I think there is no criterion when a one-dimensional singularity is a finite coinvolved. There are all the partial results. For instance, when this order is local or something like this, but not determined.
This is the non-commutative. Yes.
On the contrary, for surfaces, now I go to surfaces. Surface there.
For entering the reason
Yeah,
why
right.
you stopped.
It means that
So there is a question.
Eh?
There is a question.
Yeah.
The reason why you stopped in dimension 2 is because in
Sorry?
dimension, the reason why in the commutative story you stopped in dimension 2 is because not much is known in dimension
No, not much is known about it. Anyway, something just to remember there. Practical law is known for surfaces. For hypersurfaces, I'm not sure that everything, but it seems to me almost everything. Yeah, but not. There are examples, there are partial results. Yeah, on the contrary, for surface singularity, finite case is done. It will for maximal orders. By Arkin. And in for so-called normal orders. By Reiten and Vandenberg. What is normal? Normal means that for any prime ideal of R of height 1, the localization is hereditary. That means of global dimension. Actually, it is an analog of isolated singularity. In commutative case, it means that singularity is isolated. Maybe one should call these singularities isolated, but namely the answer. Arkin has a complete description, explicit description. Reiten and Vandenberg describes how slender Reiten quivers, and moreover, I will formulate the one result of Reiten and Vandenberg, namely A is of Cohen-Macaulay finite, if and only its category of Cohen-Macaulay modules is equivalent to the category of Cohen-Macaulay modules for the following current. We must take No. It's wrong. We must take first product with some cocycle over G, where G is finite subgroup in J2. And gamma is a cocycle, two cocycle of G with coefficients in multiplicative group. So it is very much like commutative case. Everything is reduced to finite subgroups. That means that the category of point Macaulay models here and here are the same. It is not Morita equivalence. This is not Morita equivalence, but almost Morita. And it cannot be Morita equivalent because this is regular. This guy is regular. Okay. And by the way, I also want to Chen and Ingalls. They obtained an explicit description with one more restriction. Namely, here we suppose that it is hereditary, but Chen and Ingalls suppose that the ideal, the radical, is two-sided principle, left principle and right principle. It is not a very strict restriction, but it is there are examples of this. Okay, that's what is no. Not very. No. Now what I'm going to show is also construction. First of all, suppose that we have this thing, this square R A, R. Now let it be. This is A old. I consider it's better to consider it as vertex. A vertex in the scheme spectrum R, and A is a sheaf. Okay, algebra of OX algebras coherent. Okay. Now what we can consider resolutions. We take it's a pair X tilde A tilde with the same A tilde a sheaf. And X tilde is some surface. Not all. Yeah. Is a sheaf. Algebras again coherent. And take a surjection to X A. What is that? The phi is a resolution of singularity. Singularity of X. And what else? We have also pi star from pi minus 1 a tilde. And it is birational. What does it mean? You see, we have this k, the field of fractions of x, and the same, certainly, the field of fractions for x tilde. And then we have k tensor a and k tensor a tilde. And we have, so this is, we have this map, and it must be isomorph. And moreover, certainly a tilde might be a resolution, and a tilde must be regular. That means that global dimension. A tilde must be. This is a resolution, commutative case, and the chain and inverse showed that there is such resolution always exists. And moreover, it can be obtained by the risky procedure. Blow up points plus normalization. Normalization means take over. It can be done just as commutative case. Well, so we have this solution. Usually, certainly we have exceptional cycle of 0, exceptional cycle x theta, and we have, if we cross out exceptional cycle, then pi makes it isomorphical of x minus 0. So we have this exceptional cycle. Well, yeah. Okay, again, just in the commutative case, we have this map of coin. We have a map from Cohen-Macaulay models over A to Cohen-Macaulay models over shift of Cohen-Macaulay models for A tilde, which is the same. Since A tilde is regular as vector bundles over A tilde, what is vector bundles? It's locally projective model. Projective.
So I'm sorry.
Yeah.
So what is the definition of regular in dimension 2?
Is dimension 2, global dimension 2.
Okay, global dimension.
Yeah.
Okay.
This is definition. It it's important the global dimension coincides with geometrical dimension. Because even in one-dimensional case, there are a lot of examples of orders with arbitrary finite global dimension, which is not good. Okay. In what cases I will denote by dev, by deg of n. We must take our image and then twice dual, where and dual is just home. And it is always with spectrum bundle. And so we have this. And the image of pi we call full vector bundles. There is a good criterion why when it is full. Now, first of all, it's more or less clear that it is equivalence of to full vector bundles. And then the criterion when F is full, if and only if, first of all, F is generically globally generated, which means globally generated outside finite manifolds. And the map H the map from global sections to global sections over this good part is subjective. Actually, equivalent condition is the following if we take the first local cohomologies of F to complete one-dimensional cohomologies, this map must be checked. And that's because we have exact sequence which relates. Okay, but nevertheless, it's a question how to describe it. Now suppose that there is a sheaf of ideas in A tilde supported on exceptional cipher. And suppose that it is locally biprincipial.
So there is a question, so
Yes.
it's equivalent definition, so you say,
X tilde minus E, the second.
so you have a map from the local cohomology to X tilde minus E, minus exceptional divisor.
So gamma X tilde minus E.
No, here minus, here to X tilde. You see, we have a map. Which one?
No, exactly.
Yeah, from here to here, then from here to here, and from here to here.
But what is the second
So
step?
if it is subjective, then it is injective,
second
and
is
vice versa.
The
X minus.
They actually are related.
Yeah, so that's,
Short
that's
sequence
the
like this.
notation, okay.
They are quite short sets, so it is equivalent. It is not a claim, it is well known. Locally by principle means that for any point of X tilde, there is a open, affine neighborhood such that the restrictions on U is left and right principle. Okay. Well, that's one thing. And now the main definition. We call I a reduction cycle. If the following conditions coincide. First of all, I is generically globally generated. And second, yeah, yes. Oh yeah. Yes, yes. No. It is a weekly reduction cycle. H1 is the I. Oh no. You see, I am definitely wrong. I denote by I the quotient of I modulo I square. It is a model that is lambda, where lambda is the shape of lambda modulus, where lambda is a tilde over I. So, first of all, it is about this. I is generically globally generated. And second, H1 it is with reduction side, and what is reduction side? Then we must add another one. If we take what? Check. Oh no, not this one. We must take home. Is also generically this omega lambda is just the dualizing shift, which is in our case, we can write it as home overrated due to if it is by principle, otherwise. Okay, so this is reduction side. One can do the same on the level of equivalent if we have this one, then we have cone reduction. We have a functor rho k from vector from Cohen-Macaulay modulus over A to vector bundles over lambda. Namely, we take n, take this let it be n theta. It is Cohen-Macaulay over A. It is called vector bundle over A theta. And then we just reduce this to lambda. Okay, then, which is vector bundle over lambda. Locally free. Shape of one. And the image we call full vector bundles with lambda. And the question is, there are two questions. What is this? And second, whether rho k reflects isomorphism. So we can try to describe it in some cases. When you want to reduce the cycle. First of all, let's eye the weak reduction cycle. Then a vector bundle F over lambda is full if and only if corresponds to, first of all, F must be generically globally generated. And then there is, I think, H0 E I to H1 it must be injected. However, where it comes from? This guy must comes from exact sequence following. No. E check, sorry. E check. And check where F2 is a lift of F to lambda 2, which is a delta over I squared. There must be such lift that this is injected. It is a rather complicated condition, but it's not so easy. And this is description. Then if I is a reduction cycle, then rho K reflects isomorphism. So we obtain one-to-one correspondence between Cohen-Macaulay modules and vector bundles over lambda. A full vector bundles. So satisfying these conditions. Actually, there are two parts. First of all, if f comes from some f tilde, from some f over a tilde, and f2 is f over a tilde lambda 2, yeah, and then f is full, and hence f is full. If and only if we have these two conditions. If we know that f and f2 comes from somewhere, then everything is okay. But then since we are in dimension 1, we can always lift f to f2, then to f3, to some f2, then to some f3. Why? It is known from Grothendieck that obstructions for such lifting are in H2. And there is no H2 in dimension 1. It is, actually, it can be explained even more rudimentary, but now so what we can do lift. Yeah. If we already have this lift, it is given. Yeah, in our definition. Then we just construct F3, F4, and so on, and take inverse limit. And it will be a formal lift. Okay. But again, some results of Grothendieck show that it gives algebraic which is full due to these conditions. Because we are only interested in this part. So we can lift here as we okay. So in any case we have this. But now the question is why the important why rho K reflects isomorphism. Namely, the claim is we have for reduction cycle. All lifts have k plus 1 of fk are unique. It really comes from the, I will just, we have the following thing. With subscripts. Now where H is from H to from over ja, just overlook it. Where I n is just I and I n plus 1. Yeah, but since we have f, it is the same as called 1 time of f to I n. So we have, and I recall that we have what? What do we have? We have the following. We have H. We have the following. Of Fk. This is just really automatic, not it's shifted sections. Take sections. And automatic. K plus 1. Then we have this one will be X. Then we will have H1. H1 and H1. These guys show non-uniqueness of it. And this is, we do it by induction, so it is trivial. Well, and what we have, we must know here the action of out action. Yeah, orbits of one function. And so they are sitting here. Because we must show that here is a unique whole. But then it is enough to show how x this delta. If we consider delta of the following thing, one see that it is just as delta n of phi, where delta n is a map of what? Yeah. Yes. From Andre, yes. Yeah. This one. And I will mention that they're using that effect that theta is injected. We get that delta n restricted on which one? I know. Delta n is subject. But it is not enough. Why? Because not all these, if we take phi any, but not always it will give here automorphism. But this is automorphism if k bigger than 1. So if we lift second to third, also on. But on the first level, it is not. But nevertheless, the set of phi such that 1 plus phi is isomorphism, is open, always. So its image here will be open. And then we have the orbit of F2 is open. For any F2, does not matter which. But then it is unique. Yeah. To open orbit intercepts. So that's why we have this theory. Well, there is one special case, very restrictive, but the question is that these conditions are not as special. The first one is more or less, but the second condition is very special. Case is the following: when I is such that lambda, which is I, a tilde over I, coincides with Z, which is the center. And is a reduced curve of arithmetic genus 1. Then f from vector bounds over z here is full if and only if it has a very special form. It decomposes as g plus several times z, such that g is generically locally generated. Now this one is also. Then h1 H0, and what about this M? M is bigger or equal than dimension H0 of I twisted by what? Yeah. I check, twisted by I check. So when it is reduced this thing, then these conditions can be easily verified. But having this result, we called it, it was our specialist, we called it good reduction cycle, good elliptic cycle. And good elliptic singularity. So for good elliptic singularities, we can solve the problem. And the result is the following. If we have a good elliptic singularity, it is obtained if and only if this E is either smooth elliptic or layers. Not just since the result is just for the case, the answer is also the same. There is, of course, a problem, an interesting question. How can we obtain something in the case when this is not central? This reduction is not central. Then the first, what can it be? I recall that simple smooth elliptic curves at Cadeira cycles are just those projected curves which are tame with respect to the classification of vector bundles. This is vector bundle thing. So the question is, what if lambda is vector bundle thing? Which non-commutative curves are vector bundle K? And there are results on this in this direction. Anyway, says, okay, can we obtain something like this last criterion? I don't know, but it is indeed okay. Thank you very much. Thank you very much.